Today we will talk about the next imaging modality, which is computed tomography and X-ray microscopy. We will cover also, which is synchrotron-based, as I explained to you in the first class. So let's again go back to our eggs. So we have already covered a couple of modalities. So last class we did ultrasonic imaging, where you can nicely see that you get a very, very nice resolution in the direction of the scan line, which is horizontally in this case. And you see this very, very typical speckle pattern, which is because of the interference of backscattered pulses of the ultrasound pulses. But big disadvantage, as we said before, is because of the fact that ultrasound is reflected fully at interfaces of gas, solid, or with liquids or with soft tissues. That means that actually when we take the eggs with still the shell around it, we cannot image them with ultrasound. So we really have to first take off the shell. And so that's obviously a disadvantage of it. Now, in the first class, we talked about these images here. So these were the regular X-ray images. These are projection X-ray images. So where you have the source at one side, and then you let the X-ray pass through the object, and then you have a detector that will make the image. So that means that you don't have a tomogram, so you don't have cuts through it, but you can see inside. So you see the different types of tissue that are there. And what you also see is that these are reasonably crisp images. So they actually have a very good resolution, which is isotropic. So in the X and the Y direction, you have the same resolution. Today, we're going to talk about another way to use X-rays to do imaging. And that's actually what you see here. So that's computed tomography. And you already see a couple of things from these images immediately. It's like, first of all, you start to see the different components of the egg as compared to the projection. So we do get kind of tomograms, so we can make cross sections. But as you see, there is no difference between the eggs, whether they're boiled or not. And that is by the principle of X-ray imaging, as we explained before, where X-rays, what we do is we try to measure the interaction of X-rays with the atoms. So we really look at atomic concentrations, and we want to have X-ray absorption, which is predominantly by ionization, so where electrons are being kicked away from atoms as soon as the energy of the photon is big enough. So that means that we look at atomic concentrations, and obviously when you boil an egg, the atomic concentration distribution is not changing at all. What is happening is that your molecular environment is changing. And so you get that your proteins are starting to coagulate and come together. So that means that when we just look at the atoms, we can't discriminate, and that's what you clearly see. So now the question is, how do we make these images, and what are the typical properties of these computed tomography images? So that's what we're going to try to cover today. Very briefly, computed tomography is relatively young. It's already some time here, but it actually started, or originally started, from the theory. So in 1917, Radon had kind of calculated that it is possible to do imaging based on making projections, and that's what it comes down to. And the first scanners actually came in the 70s of the past century. One of the things that you see with all these imaging modalities, the same as with MRI and the same as here with CT, is that they actually got Nobel Prizes, the ones that were able to make these scanners. Because nowadays, this technology is so important in clinical medicine that it was really a big step forward that we could make these tomograms. Before that, they could only do X-ray, and as I said, that is projection. It's very difficult to look at detailed morphology that way, so the CT scanner was a big step forward. And then you see that actually over the years, and it's still going on, the CT scanners have been evolving in getting partially bigger and better resolution, and predominantly faster, and especially also with less radiation, because we still have to use X-rays, so there's still the problem of the damage that you do using ionizing radiation. Okay, so typically we make cross-sectional slices, and a typical pixel size, as I said before, would be, or image size would be, that we have 512 by 512 pixels. So again, as I said before, that's not much. So if you cover the whole cross-section of a body with just 512 pixels in each direction, the pixel size and or the resolution that we get is not that great. We'll see it's in the order of, say, roughly 0.5 millimeter. That is like the order of magnitude that we can get as a spatial resolution with a CT scan. Now, one nice thing about a CT scanner is that we can really measure X-ray absorption. So what we do is we can, the images, the value of the images that we see, the pixel value of the images, so the grayscale that we get in the images, really represents the absorption by the tissue. And it's actually being expressed in Hounsfield units. And Hounsfield units is always with regard to the absorption of water. So you compare it actually to the absorption of water in such a way that water is 0. And for example, bone becomes a very, very large value, and air, of course, becomes a very small value as compared to, because air, given that the atomic concentration of air is so low, has almost no absorption for X-rays. Now, one of the things is that because we have this very large range in absorption values, that means that actually the scanner can actually acquire values which are very, very much apart, so a very, very broad range of values. And as I told you also in the first class, is like our displays that we're using to look at these images, they're not able to show so many gray values, or at least they are not able to show this dynamic range. So we need to do some processing in order to see, or in order to emphasize in some ways what we see. And this is already something that I showed you also when we are looking at projection X-rays. So depending on what type of tissue we're looking at, we can actually look at gray values that actually cover this. And you see here, this is a cross-section. So this is a typical CT image, a cross-section through the thorax. So you see that the heart is in the middle. You see in very white or bright, you see the bones, because as we said before, calcium and bone absorbs X-rays quite a lot. So you really see nicely the spine, and you see cut-throughs through the ribs. This is like the shoulder blade. And you see immediately that the lungs are just totally black. So if we see the tissues, then you see that there's nothing to see in the lungs because they're full of air, and of course, we can't display that. So if, on the other hand, we want to look specifically at the lungs, so what we can do is we can look at the values that are specific for the lungs. We can do these settings. What you then see is you nicely see the lungs. You see the airways in the lungs. But of course, then you don't see the rest anymore. And what you also see now is that you emphasize these structures here and around it. So these are actually the parts of the scanner. So this is actually the bed of the scanner where a patient is in, and on top of that is actually like a kind of a mattress in order to keep the patient comfortable. And what you see here, this is just a cover, some kind of clothes, or mostly they ask the patient to wear a gown, for example, when they go into the scanner. So you see already that depending on what we want to look at, we might have to use some processing which is relevant for what we're looking at. Okay, what do these scanners look like? Well, in the end, what we need to do is, in order to do X-ray imaging, as we said before, we have to measure X-ray absorption. So that means that we have to have X-rays at one side of the object being produced. They have to pass through the object, and then we have to measure them with some kind of detector. And so a typical way of doing that, so the difference between the regular X-ray, so like X-ray thorax and the projection X-ray that we said before, and CT, is that we're going to make projections from all directions. So what we're going to do is we're going to take a source. We're going to take an X-ray source. We're going to take a detector. we're first going to measure in one direction. We're going to measure individual lines of projections. So we send out an X-ray and we receive it or we measure it. And so we let the detector go in that direction. And what we then do is then we rotate the detector. And so we keep on rotating the detector, and each time make sure that we have like a full projection from that direction. So typically we go under 360 degrees. So we really turn around the object. Theoretically, 180 degrees is enough, because as you know, if you go from the X-rays from the top to the bottom, or the X-rays from the bottom to the top, you cross exactly through the same amount of atoms and the same atoms. So that means that the absorption would be exactly the same if you go in one direction or the other. Very often we do the 360 degrees in order to get like a better signal to noise ratio, for example. Now, we can, of course, simplify this in a way, so we don't need like a line source. What you can do is you can take like a fan source. So that means that your X-rays can fan out and we measure several points at the same time. Or we can do a full fan. So we really have an X-ray kind of source which is sending photons in these different directions. And then we can put an array of detectors here. And that means that just in one shot of X-ray, we have one projection, and then we can go in the other way. So this is typically what is being used nowadays. So that means that we have actually a detector which is going around the patient and is continuously sending out X-rays in like a fan-shaped kind of field. And we measure that with the detector, which is also rotating, obviously. So what is rotating is both the X-ray source and the detector, and they rotate totally around the patient. Now, the detectors themselves, well, it's similar to what I've been saying with X-ray imaging. Is, of course, obviously, since this is computed tomography, so that means that with all these projections themselves, we can't see the image. We have to do some computing, the reconstruction. We have to do that in order to have an interpretable image. So we'll explain that in a minute. But in order to be able to compute, of course, we need to have these values in a digital way. So we need to kind of sample these values. And that means that we actually use digital detectors. So from the beginning of CT, there were digital detectors. And as we said before, digital detectors are mostly based on scintillation, and then later on a photodiode. So scintillation, what happens is your X-ray photon comes into the scintillating material. There, the X-ray photon is being converted into a visible light photon, and that visible light photon is then being captured by the photodiode and is then being converted into an electrical current. That's the really typical type of detectors that we use. And there's many materials nowadays that you can have, can be based on cadmium, yttrium, cesium, gadolinium. So there's all different types of detectors. Now, that's the very typical one. But of course, what these do is they make no difference between which type of photons are coming in. So you can't detect individual photons, and you can't detect their energy neither. So, and as we said before, you have a very wide range of energy of different energies of the photons that are being produced by a vacuum tube, an X-ray tube. So as we showed before, the X-ray tube, so based on the principle where we accelerate electrons in a vacuum tube, which then bump into a metal plate, send out a whole spectrum of X-rays. So that is like a whole spectrum. When we do this type of photodiode and scintillation, obviously we just detect that there is X-rays coming in. We don't know exactly how many, although of course the intensity is proportional to the amount of photons that are being captured there. And we cannot distinguish their energy. We just measure them, that's all. So what you have nowadays is that actually photon counting detectors are being specifically developed. There's a lot of development of this in nuclear medicine. That's now also slowly coming into the CT and the X-ray part, but still, this is still kind of experimental in some way. Right? So the regular clinical scanners that we have now are all based on this integration. So they just measure the intensity of the X-rays that would come in. Okay, so how are we now going to do imaging using this principle? Right? So how can we make a cross-section of the body by having an X-ray that passes through and let them pass through of all directions? Well, first, let's then see, it's like, what are we actually measuring? Eh? And as you can remember from the first class, so what happens is that the intensity of X-rays that we measure at the other side of the body is related obviously to the initial intensity. Yeah? So the more X-rays we kind of let produce and let pass through the body, the more we will measure. But they will be attenuated with an exponential, which is related to the X-ray attenuation coefficient. And obviously, since we're talking about kind of non-homogeneous tissues, so that means that we have different types of tissue, different types of organs. So we have a whole kind of distribution of different types of tissues here. What we need to do is we need to integrate over on every position that that we pass through. So it's like a line integral under a certain angle, so angle theta, going over the radius of this line, and then integrate over all the local attenuation coefficients. So that gives us then the intensity that we measure for a certain angle. So if we look at a different angle, obviously it will be different because this line integral will be different. So what we actually also can do is we can do a transform, and this is a typical transform. It becomes later on clear why we do this transformation. And what we do is we actually don't immediately just look at the intensity, but what we do is we take a logarithm where we take the intensity and we divide it by the initial intensity. So we become independent of the initial intensity, and we're going to work in a logarithmic way, because what I told you before is there's these large differences also in the attenuation coefficients. So this gives us like a little bit a compressed way of looking at it, but that captured whatever we want to see. So next, what we do, as I said before, we want to have, of course, in a certain direction. So under this angle that we're looking at, we want to have the intensities or the projections of every line. So because we want to cover, of course, this whole thing. So this would be similar to what we do in regular X-ray imaging. So we want to have the X-ray passing through the whole body. So that means that we have several lines that the X-rays pass through. And for each of these lines, we measure the intensity. So of course, the initial intensity here was the same for all of these, but the intensity that we measure will be different depending on where we pass through. And so a typical intensity profile might be here. So what we have is for a certain angle theta in this direction with a certain distribution. So we have a spatial distribution of the attenuation coefficients. Well, this is actually what we want to measure, because we want to measure the different types of tissue. So we want to measure the different attenuation coefficients. And so we want to try to recover these. But what we measure in reality is, of course, these projections. So what we measure is we measure the intensity of the X-ray that passed through the line in this direction. And so we get a typical profile like this. So, and each time the value here is, as we said before, the exponential of the line integral over all the points that the X-ray beam passed through. This is for one theta, we get this one profile. As we said before, we're going to convert this with this logarithmic transformation. And what you now can prove is that actually what we actually are measuring, so if we take this transformation, and because this is the logarithm, we can actually rewrite it as this function of the attenuation coefficient at the points R, so alongside the line, and the angles, and that with kind of a sine wave. Now you start to see that this type of expressions mathematically starts to become starts to look familiar in some ways. So this is going to come close to things like Fourier transforms. And we're going to see later on that the Fourier transform is actually crucial for the reconstruction from projections. So this is what we measure for one angle that we go pass through the object and over the whole kind of side of the object. So we have the X-ray source. Under a certain angle, it passes through. So we have this angle, and each scan line there that we have is at a value of at a position R for that angle. Okay, so when we now start to express this a little bit more, just a thing to also remind you is like, I don't expect you to learn all these formulas by heart. You will see later on in the practice that you will use some of these formulas in order to do calculations. But what I want you to know is the general principle, what is behind it. So what is, for example, this intensity and the line integrals, and what is a projection and things like that. So these are the things which are important. So what we now say is that for a certain function, so for this kind of function that we measure as a function of the r and the theta, we can write this formula, and this is what we call the radon transform. And so this is a general formula, but of course what we said before is that we do this for the attenuation coefficients, for the X-ray attenuation coefficients. So how do we go now to images in this way? Because that's in the end what we want. We want an image of a cross-section. So the first thing is that we can actually already visualize, if we're going to make projections from different angles, we can actually visualize this already in some way in an image. And the image is what we call a sinogram. And so what we do is we convert this. So let me go back. So this measurement, so this is the measurement in one direction. So this is the projection or the transformed projection in one direction. As I said before, what we're going to do is we're going to measure this in all the different angles, so in the different projections. So one of these projections, so as we said before, so you measure this, so this is related to the attenuation, to the intensity that comes out after the X-ray passed through the body, and we can convert this into a grayscale. So what we do is, instead of plotting it like this, what we do is the higher the amplitude, the whiter the pixel will be, and the lower the amplitude, and if it's 0, then it's black. So what we then can do, so we can take one of these lines and we can plot it here. And then we can take the next angle and the next angle and the next angle. And so what we do is we horizontally plot all these different lines. So what we measure, the projections, we put that in this image. So we get an image which is on the one hand has in the x direction has like this r direction, so that is the position on the radius, so of the projection of the detector in some way, because that is the position on the detector, which is then moving around at a certain angle. And so here in this direction, so we have the angle. And so what we get typically, so, and you can see why it looks like this. So it's called a sinogram because this looks like a little bit like that you get sines. But why do you get this? Well, for that you can take like a simple example where we say is like, say that our object that we measure is just one dot. So it would be say one dot or one piece of bone or whatever. So one dot which is highly absorbent for X-rays. So and now we're going to make projections. So if we first make the projection in direction 1, so that means we put the X-ray source on top, we let it pass through the object, and we measure it here. Obviously, it will be black everywhere here, except here. we will have a big white dot. So that's this white dot, because here absorption will be very high, which means that the intensity will be very low, which means that then this kind of transformed one will be bright. So then we're going to start rotating our source. And for example, if we are at this position 2, so that means that the X-ray source is here and the detector is there, what we now see is that given that the detector is here, obviously this white dot is going to project here. And what we see now is that, of course, this moves much more to the middle of our detector. So if the X-ray source is here, the detector would be here. What you see is that this projection almost comes to the middle. So we see that it's projected there. And so the more we turn around, what you see is that actually it shifts a little bit. And then at 4, for example, it looks like the projection would be at the other side. And so you can make it see clearly that if we have a point which is not totally in the middle of the object, and we turn around our X-ray source and our detector, what we will see is that in the different projections, we will measure this point as a big attenuation, as this kind of sine wave. Is that clear for everybody? Because that's an important concept.
Can you repeat the projections of a dot?
So we want to make projections of all directions. So we want to go around. So we have this object. So the dot is somewhere located there. So we want to go with our X-ray source and our detector. We're going to go around this object. That's the idea. And we're going to plot each time the intensity that we measure. Well, actually the inverse of the intensity that we measure, or like the logarithmic transform of this intensity, we're going to plot that as a horizontal line in the image. So we're going to go around, and every time we measure a projection, and the projection that we measure in our detector, we're going to put as a horizontal line, consecutive horizontal lines on our. So if we have the X-ray source, in this case, on top, and we have the detector on the bottom. In this case, if this point is located here, it's located a little bit to the right, not in the middle, a bit to the right. So that means that that projection will, if we look at the detector, will be 0 everywhere where we go through air, and will be high at the moment that the X-ray passes through this dot. Then the X-ray is almost fully absorbed. And when it's fully absorbed, then we have this very high p-value. So we have a very low intensity that becomes a very high p-value, as we said before, because we do this logarithmic transform. So we measure the high absorption here, and if we plot that in a horizontal line in the image, it will be a white dot there. Now, if we start moving the X-ray source around this object, what you will see is that, of course, with regard to the center of our detector and the center of our X-ray source, by the fact that this dot was at an asymmetric position, what happens is that, of course, it becomes more and more to the middle. So in such a way that if our detector or our X-ray source would be here and the detector would be here, this projection would fall exactly in the middle of the detector. And that is around position direction 2, maybe a little bit further. So in this direction here, so at the moment that the X-ray source is there and we project there, we see that that dot, or the projection of that dot, has moved more and more to the middle of the detector. And if we then keep on rotating, then of course it moves in the other direction. And here, this position, so this exact disposition is when the X-ray source is at the bottom, and then the detector is at the top. Then we see that this projection flipped. So if we turn under 360 degrees, what we see is that the projection of this dot is starting to change the position in the R direction, which is the position on the detector. Where on the detector do we see the projection of this dot? That is going to shift when we turn around. For a dot that would be exactly in the middle, of course, we would have a white line, which would just be a vertical line in the middle, because then, of course, it would always fall in the middle of the detector. And the further away to the side this dot will be, the larger the amplitude of the sine wave would be. And so here what we see is we see the sinogram of a more complex object. So this is a complex object that had a very high absorbing dot somewhere asymmetrically. And so we see here that this high projection is from one specific dot, the other high projection also, and you see some more. So you see some with a high absorption, and then you see also many lines with lower absorption. And you see the outside, so you see that here the outsides are black, which means that there are some kind of lines, so that there's like a circle of air around. Is that more or less clear?
Yes, thank you.
So this way we get the sinogram. And that is actually, this is what we measure. So this is the image that comes out of the scanner when we measure it. Obviously, we cannot interpret this, so this makes no sense, because actually this is an image of a brain of a patient, of the head of the patient with the brain inside, but we can't see anything. So we need to somehow try to convert this into something that we understand. And so what we need to do is we need to try to see whether we can recover, whether we can calculate the attenuation coefficients or the distribution of attenuation coefficients in space that caused the sinogram. Okay, so now one way in order to do that, and that's in some way the most straightforward way, is that we're going to do what's called back projection. So what we know now is that we know that if we measure a point, say that, for example, on the detector, so if we look at the line which was taken by the X-ray being on top and the detector being on the bottom, so that means this kind of line 1, so point 1, so this direction 1, so this point we have measured. And what you know is that the measured projection has to come from this line. So we measured when the X-ray source was on top, the detector was on the bottom. We measured this high value here. So we know for sure that this high value comes from a point that absorbs, that was somewhere on this line. However, we don't know where. So that's the same, that's with a projection. With the X-ray projection imaging, what we see is we can see through the body, but we don't know exactly at which depth we're looking at. So we have no information on the depth. But we do know that it has to come from this line. So what we then do is in our reconstructed image, what we say is like, okay, because we don't know where it comes from, that means that all the positions have an equal probability to have the point that was there in reality. So what we do is we smear out our projection over all these values. And so we say that, okay, here in this line, somewhere there's an image, there is an object, and we say like, okay, let's distribute the value that we measured over this whole line. And we do that for all directions. So here in this direction 2, we measured when the detector was here, we measured the bright spot here. We know, since we measured the angle, of course, at which that we did the projection, so we know that it has to be on this line. So let's smear it out. And if we smear out all the projections of these different directions, what we actually start to see is that in the position where the point exactly was, of course, we're going to have a much higher value, because this is where all these smeared out lines come together. And so in the end, if we have like ideally an infinite amount of projections, what we see is that in the end, the value here becomes much higher, because that's where all the projections add up. So this way, what you see is that if we had this dot, this is what we measured. So with a distribution of the attenuation coefficient, which was like this, no attenuation surrounding it, high attenuation in this dot. If we do this back projection, what happens is that we get this type of distribution. So we see that most of the values that we have smeared out come together in this point, exactly what we want. But of course, by the fact that we had to smear it out in order to do this, because we didn't have information exactly on where they came from, what you see is that we get like a smoothed version. So this way, we can reconstruct the object, but keep in mind that there's a disadvantage of that it's smeared out. So this is a most straightforward way of doing the reconstruction. So this way, we have an idea of the distribution of the attenuation coefficients that was measured, but with the disadvantage that it's a little bit smoothed. Now, one problem, obviously, is that we don't have an infinite amount of projections, and also we don't have an infinite resolution or an infinite number of pixels that we want to reconstruct. So that means that this will always be discrete. So instead of what we said, like mathematically, what you can do is actually this is an integral. So again, you're going to smear this out. What we now have to assume, of course, that it's a sum of all the pixels. And there is one big disadvantage also with this, is that because we work under different angles, so we actually measure in a polar coordinate system. So we measure under an angle over a distance on a radius. But of course, the image that we want, so the image of the cross-section of the body, we want that in a Cartesian coordinate system. So we have to convert the data, which is under an angle and a distance on the detector, into data which is at a XY Cartesian grid. So that means that obviously we need to do interpolations. So if we want to measure or we want to calculate or redistribute values on this line, what we need to do is we have to interpolate between two pixels that we actually measured. So these are the individual crystals on the detector, so where we did the measurements, and we need to smear that out. Now, interpolation, and especially interpolation under different angles, is something which is in a way tricky. It's something that we try to, or we ideally would try to avoid as much as possible. Sometimes it's unavoidable, but it's computational costly, and also you need to put an interpolation function, which you don't really know. So now we're going to see is whether there's different ways, whether there are other ways in order to do the reconstruction. Instead of just doing this back projection, where we have the disadvantage that it's being smeared out, can we do it in different ways? Can we find ways to make this more accurate or more efficient in some ways to do? Now, one of the things that if you start to look at these formulas, what you now actually can prove is that if we have the sinogram, so which is this kind of P, what you can prove is that actually the Fourier transform of the sinogram and the Fourier transform of the distribution of the attenuation coefficient in a Cartesian system, they are actually equal. The only thing is that they are in a different coordinate system. So that means that if you take the Fourier transform of your projection, so of the P, you then convert it from a polar to a Cartesian coordinate system in the Fourier space, and you then do an inverse Fourier transform of this, you have your original distribution. And that's the kind of famous projection theorem for reconstruction from projections. So the theorem says, as I said before, we don't need to go into the mathematics, but conceptually it says that we measure the sinogram, we take the Fourier transform of the sinogram, we convert it from polar to Cartesian coordinates, we take the inverse Fourier transform, and we have exactly our original distribution of the attenuation coefficients. And so that means now that we can do image reconstruction by using Fourier transforms and inverse Fourier transforms. And this is exactly what is being used mostly for CT. As I said before, we're going to go in more detail in this in the practica. So we're going to see how this works, but this is the basic principle. So this is what I said. So the direct Fourier reconstruction is take the Fourier transform of the sinogram and convert it into from this polar coordinate system. So in Fourier space, this is what we call K space. That's also being used in magnetic resonance imaging. So magnetic resonance imaging actually also uses Fourier-based reconstruction. So the Fourier theorem is very, very important for medical imaging. So this would be the points that we have measured in the Fourier space of our sinogram. If we then interpolate this into a Cartesian system and then do the inverse Fourier transform, we have our original distribution. Fourier transforms are computationally very efficient because we have the fast Fourier transform and we have that in integrated circuits and things like that. So calculation of Fourier transforms is easy. The only problem is here again that we need to do interpolation. And as I said before, interpolation is something that you would try to avoid if possible. And so there are actually ways in order to avoid this, and ways to avoid it is actually using filtered back projections. Again, the theory is not the most important, but what we can do is if we filter first this Fourier domain of the projections, then we can actually calculate this much more efficient. Then we don't need to do this interpolation. As I said before, we will practice a little bit on this in the practica. So this is what is done predominantly in most CT scanners. So what happens is we measure the projections, we do a fast Fourier transform, we filter the projections, and then we do an inverse Fourier transform, and then we get actually the reconstructed image. Now, this theorem that I've said before is for a projection of parallel X-ray beams. Yeah? But parallel X-ray beams would assume that either we have an X-ray source which is moving for each projection over a line, or we have an X-ray source which is very, very broad, and neither of these is practical. So what we work in reality with is what's shown here. So we work with fan beams. So we have an X-ray source, which is more or less a point that sends out X-rays in like a fan shape. And we have a broad detector that is measuring all these different projections. But obviously now our projections are not coming from parallel lines anymore, but from diverging lines. So that means actually that, of course, our reconstruction, we have to take that into account. And so you can write the basic geometric composition of these beams. You can actually write a reconstruction. As I said, this is also not important to go from the mathematics, but you just have to keep that in mind, that in reality, it's a little bit more complex than just purely the filtered reconstruction, of course. Okay, so now we had two ways of reconstructing our data. Is one, we do the pure back projection where we smear out the measured projections from all directions. And then we have a smoothed version of the image, but this gives us an image. Or the other one is where we use the projection theorem, where we know that there's a relationship between the Fourier transforms of the projections and the Fourier transform of the original image, of the original distribution. So that is the basic principle of that reconstruction. Now, there is a third way of doing this. And this is actually called iterative reconstruction. And the idea here is that, so we have measured the projections, and the projections are the result of projecting X-rays over a distribution of attenuation coefficients. And what we need to do is we need to find back the original attenuation coefficients. So we have a body. A body consists of different organs. Every organ has different attenuation coefficients. That's what we want to measure. So we want to make an image of the spatial distribution of these attenuation coefficients. What we measure with the scanner is the projection of X-rays that pass through object with this certain distribution of attenuation coefficients. So we measure the projections and we want to reconstruct the distribution. So what we actually can now do is trying to see is like, okay, can we find the most likely distributions of attenuation coefficients that will give us, if we use a scanner, this projection. So that's the whole idea of iterative reconstruction. So what we're going to do is we're going to measure projections with a real scanner, and then we're going to use a virtual scanner where we start to see whether we can find a configuration, a kind of representation of the body that would give us very similar projections. And that's actually being expressed here. So we have the measurement, that's our sinogram. So this is what we measured with a real scanner. So what we do is we say first, it's like, okay, we don't know anything about the body that's being worked out. So let's say that the distribution is just a circle of attenuation coefficients everywhere. Say that it was homogeneous. So we say here that it was the real distribution would be this kind of gray circle of distribution. Now, what we now can do is we can say like, okay, if this was our object, then if we would scan this object, what would the projection look like? So we make here a virtual scanner. So this is actually a software scanner that we make here. So, and with this software scanner, we would project this distribution, and we get this fully gray sinogram. That's what we would get first. Obviously, this is not correct, because what we can do now is we can compare this with this. And we say, okay, it's wrong. So there's something wrong with our distribution. And what you now can do is you can compare the two, and you can write a mathematical equation in order to update it. So saying like, okay, it's so different and like everywhere it's different. So let's kind of change this distribution, knowing that there has to be something here and this needs to be black. Let's see that we adapt our object or our distribution, knowing how different this is. So we have an update now. We say like, okay, it wasn't this distribution, but maybe it was this one. And what you then do is say, okay, let's just measure this with our virtual scanner. Then we can get this sinogram. We can again compare and say like, no, it's not good enough yet. Oh, it's better because it starts to look closer. It's not good enough yet. Let's update. And then we assume, okay, maybe this was the distribution that we measured. Again, we put this through the scanner and we get the next sinogram. And this way, we keep on going around. We keep on updating our assumed distribution of attenuation coefficients up to the point that the projection, so that the scanning of this virtual object gives us something which is very, very close to what we actually measured. And then we assume that indeed what we measured would correspond to this. And so the idea is find, given the measurement that we have, given the real measurement that we have, find the most likely distribution of attenuation coefficients that can give this projection. And so it's a total different principle. So where the principle of the Fourier transform reconstruction really is mathematically correct. So there you say, okay, mathematically, these values, what I measure is related to what I want to know, to my original distribution through these formulas and calculate these formulas. What you're going to do here now is saying like, okay, we have a measurement. Let's try to find, however, with an iterative way, so with adapting it, let's try to find what's the most likely distribution that we had that could give, if we would scan it, that would give the sinogram. Obviously, this is computationally expensive. You need to do a lot of calculations. So this is much more expensive than doing just Fourier transforms, even if you would do interpolation. Because you need to do, every time you need to do the software scanning, and then you need to do the comparison. But these projections, of course, are relatively expensive to calculate, because of course you need to calculate the projections from all directions. But this has a very important advantage also, because now you're not going to mathematically relate these two images, but you're going to just find what's the most likely. And the advantage is because if you mathematically say, this is my measurement, and let's find the theoretical distribution that you have, is if you have noise in your measurements, then obviously you would reconstruct the noise. So because theoretically, what is measured, that is measured. While here, what you can do is you can actually somehow compensate for the fact that there is noise. When you do this comparison, you could say like, look, okay, it should be as close as possible, but if we know we have a certain noise distribution, it's like, let's see what's happened, and then we can kind of take that into account. Or what also is the case is that if we use the theoretical reconstruction, what we assume is that this measurement is perfect, which means that the scanner has to be perfect, and which means that the angle that we measure has to be perfect. But you can already imagine, so this, what we need is the scanner will look like we have inside this X-ray tube, we have a detector which has to rotate. Since we need to make this engineering-wise, there will always be some kind of errors in it. So because no machine is perfect. So that means that what we actually can do is in this virtual scanner, we can actually also put the problems of the scanner. We can make this a much more realistic scanner than the ideal scanner that, of course, the Fourier reconstruction requires. Yes. You had a question? Hello? Can you please ask the question? Because
yes, sorry. Do you hear me?
Yes.
Okay. That I was wondering which criterion is used to generate these invented images that you say that then are like measured.
Yes. Well, there are several of these. I think in the last practicum also you will use some of this. You will look at this, but that's exactly what all these algorithms are. So there's different ways. I mean, in principle, you could do kind of just even subtract them and then find a way to put it, or use a back projection, for example, in order to estimate it. So there's like different ways in order to do that. And that's also why you have very, very different of these algorithms. So we're not going to go in detail in exactly what are these. At this moment, it's not that relevant. The most important is that you have to know that you compare each time the virtual projections with the real measurement. That's the most important.
I have also a question.
Yes, go ahead.
How much time can it take to reconstruct doing this technique?
Yeah, well, that's the tricky part in some ways. So if you would do that with your PC and you would have like a full CT scan, it might take several hours to do the reconstruction. Now, what happens in hospitals is what you will see is that with CT scanners, because of the fact that CT scanners are actually quite okay technically, most often still we use the filtered back projection. So there's very few scanners that use this iterative reconstruction. Except nowadays, when we look, for example, if we want to go to very low dose scanning, so if we want to reduce the X-ray dose in such a way that we actually have a lot of noise in the images, because if our intensity, our original intensity is too low, then we come in the noise level of our whole equipment, then of course we need to do iterative reconstruction. What you will see is that for nuclear medicine imaging, which uses exactly the same principle, also measuring projections now of gamma rays and not of X-rays, because nuclear medicine is so noisy, what they do is they mostly would use iterative reconstruction. But what you then see is that with the scanner, what you do is you put like a computing cluster in order to do that. So you have in the hospitals next to these scanners, it can either use a local hospital scanner, or it can use a computing cluster, which is with the scanner. But so it is a very computational intensive task. Also, it depends again then how much time you have. So sometimes what could be is that you make a quick reconstruction with filter back projection, and then you have, say, 10 minutes or an hour, and you make the more detailed reconstruction, because it could be that if it's not an urgent scan, that a radiologist would read the image just the next day or a couple of hours later, and so on. So, but this is for full scans, mostly not real time, unless you really have big supercomputers behind it. So it's again this balance between cost and efficiency. And as I said before, if you work with relatively high dose CT, as you can do in elderly people, then the dose is not that relevant anymore. So then you can do it faster or with simpler reconstructions. If you go to noisy environments, you really need to do this, and then you just need the time or need to spend money in order to buy the supercomputer.